So I was considering this um, space covering demo. That's um, I don't know. It's this grid. There's it does a polar map over a sphere that I can increase the size of the sphere, and it stretches a polar map or a rectangular map around a sphere. Um, these orientations, the the green, which is the y direction or up, in this case, is always perpendicular to the sphere. So on the bottom they stick down, on left and right they go left and right, and at the top they go up. And this is the rotation coordinate of them. It's not very clear from this where things are. This is the origin, though. And the way that this is projecting, it's projecting on basically the YZ plane. So the further out you go from the center for a rotation vector, you get more and more rotation. These are kind of not directly related to these. Like, they're kind of turned. Anyways, the original point of this was there's these various projection maps. As a polar graph, it starts in the center at 0, 0, 0 and goes out to pi. This is, 180 degrees. And then past 180 degrees, it keeps going out to 2 pi. And then it's still not coming back along its original path. Maybe it does. Okay, anyways, if we start with a small patch, this is out, 45 degrees and around 360 degrees. And this particular graph, if the spin is 180, which is kind of 1/2 of a whole turn, then that circle translates out to a distance around pi. So there's a ring that the center follows that goes around in a circle. That's at 1 pi, and it goes out to 2 pi. And then if I extend this to cover 360 degrees, past that it starts coming back along that same path from the target up to 720 degrees. So in this state, this covers the full plus 4 pi of rotations. And looking at it this way, it's basically always in a plane. And this angle is I don't know, it rotates the effective spin orientation. The from 0 to that's 1/2 pi. It's 1 pi. And 2 pi. And this is back to the origin. Right. 1 pi is half a rotation. So the angle of that plane is just directly the longitude. So that even makes it look like basic rotations. So this graph has that one line that wraps around the pole, too. But only at 0. Well, probably at others, but but this is the basis map. That's the full 2 pi of rotation space. So the inner space is, the outer sphere is projected at slightly larger than 2 pi, so that it encompasses the map and the graph of the rotation points that make up the sphere. So 0, 0, 0, 0 with this basis gives me basically a toroid. That this is the center of, oops, I'm gonna leave that. But that only works in the first octave. The second octave is still in a plane, but the origin isn't so pretty, I suppose. But then the orientation of that plane rotates. As you rotate the longitude. I think that's only rotated that plane. Okay, about 1/2 turn. And then, if the graph is just a little bigger, say 1/2, the sphere lines start to muck it up. So in both of those origins, the normals are always pointing the same direction. It's down. It looks like up and down. So these are always ups. Well, that can't be. Because these would have to be the same direction. They'd have to be the same direction all everywhere. So they're pointing down. And these are pointing up. So remember, these inner points are representing the rotation vector for this frame. I didn't really explain that very well in the beginning either.